physical chemistry. Last we had seen in knowledge area 1 about properties of gases. Now we go to the knowledge area 2, where we have kinetic theory of gases. It is a continuation of properties of gases. In this part, we will have some postulates of kinetic theory of gases, mathematical analysis of theories of gases, real gases, and last we will have the properties of gas mixtures. Kinetic theory of gases is another treatment of the properties of gases as consisting of small particles, that means atoms or molecules. There were assumptions behind that, and then the assumptions first of all was that when gases are in the container or a closed device consists of extremely small particles, which are called molecules or atoms. Another assumption was that the molecules of a gas are separated by great distances and they occupy a very small fraction of the total gas volume. As you can see that we have been treating the volume of gas with respect to the volume of a container. So when you have a 1 liter container, that is the volume of gas. If we have 2 liters, that is the volume of gas. So the assumption is that the gas molecules, the gas particles, have a very small, very great distances apart, so their total volume is negative. Another assumption was that there are no intermolecular forces and no attraction between the particles which are in the container, that they cannot attract one. So there is negligence of some van der Waals forces, or some polar bonds, if ionic bonds like that, so such forces are not assumed. So there is no interaction. Or there is no intermolecular forces between one molecule and then another one. Another assumption was that molecules are constantly moving in a random motion, with the results in frequent collisions between one another and with the ball. That when they are in the container, they continuously do move, but they move random. They collide with the walls, but they collide also with one another. And of course, the collision with the wall is the one that results into exertion of pressure, and sometimes it is a rise of temperature. It means that there is effect in increase of volume. Expands. The vessel, the device expands or increases the volume. Another assumption was that when there are collisions, the collisions are elastic. There is no loss of energy when there is collision. The ball and one, there is no loss of energy. So there is a mathematical analysis of kinetic theory where a container is assumed, which is a cube. a cube having a length L and containing the amount of molecules N of the gases. And those, that amount of gas has the mass M, but are in a cube like that. Now, so we have a molecule which is in a cube, and such a molecule, when it is in a cube, it is of course with the another molecules that they are moving randomly, but their motion, since a cube is a three-dimensional figure, so we expect that if we assume one molecule, it will have a motion which is along the axis, in one direction, so it can have another direction along the y-axis, and it can have also another direction which is in the z-axis. Here the objective at the end, we have to find how the molecules exert pressure in this cube which has a certain volume V with the length is L. And at the end, try to find out the energy of a molecule when it is present, when it is moving in that cube. So there is, we expect that the volume will be reversed since we have the lengths being equal. So that cube will have a volume with the L cubed, where we expect that when a molecule is moving in that cube, it will have a momentum. We have a momentum in one direction, which is represented by mass times velocity. In one direction, mass times velocity along the axis, which is equal to mass times velocity along the y-axis equal to mass times velocity along the z-axis. So that's the assumption that in all directions the molecule will be moving with the same velocity. If we take one component of velocity, of course, we consider only one dimension, that it is moving along the x-axis, then it will have the momentum before collision, which is presented as nu, and after collision we will have a negative mu that is moving in the opposite direction. So the change in momentum will be mu x minus mu y, mu x that gives out 2 mu. That's the change in the momentum. Now we are interested also to know what will be the force. The force there is considered as the rate of change of momentum. We have the rate of change of momentum, which is represented as mux squared over r. Then, of course, here we have the force. We have the force only along when we have the velocity along the x-axis. But we have to find out the average velocity in all axes, along the y-axis, along the z-axis, and then in computing, we see that we will have the average velocity in all components, which is given in that way, as the average velocity of x along the x will be equal to the velocity divided by 3. Now, if we substitute it in the formula of finding force, so the force will be represented as the mass times velocity divided by 3L. Yeah. The interest is on pressure. Which pressure will be exerted by that molecule that is moving along the x-axis. So there, we know that pressure is force over area, and then we have there the area. So at the end, because we have already the force there, if we substitute, we will have pressure being represented in that way, where we will have at the end having pressure as a mass times the velocity squared divided by 3 times volume. Now we are considering only one molecule. If we have n molecules, then the total pressure of n molecules, we will have to multiply by that number of molecules. So we end up having the pressure. The pressure is equal to number of molecules times mass of a molecule times velocity, average velocity, over 3 times volume. Yeah. If we rearrange there, we will have PV is equal to number of molecules times mass times velocity, average velocity squared over 3. We have here to know that we had a molecule with a certain mass, which is not valid, and we will have also a number of molecules which are contained in a cube, n, and we will have the velocity of a molecule, the average velocity of a molecule, which is u. All of them are constant, divided by 3. So we say that PV is equal to constant. So in another way, we say that in this derivation, we are trying to prove the Boyle's law, where we have that volume is inversely proportional to pressure. And we have PV is equal to, if we will change that into constant, then it is equal to constant. Yeah. Another important, so we have seen how pressure using the kinetic theory can be derived and having the equation. Another thing that is important there is to know the kinetic energy of molecules which are contained in that cube. We have already that PV, pressure times volume, is equal to number of molecules times mass of a molecule times that average velocity divided by 3. From ideal gas equation, we know that PV is equal to NR. PV is equal to NRT. So we can say that NRT NRT is equal to N M divided by. So it is related like that. So we can have a number of moles times gas constant times temperature is equal to the amount of moles of particles or molecules times mass of the molecule times the average velocity divided by 3. Okay. Then there we can have suppose we try to rearrange the equation. We can have it as a, if we multiply by, let us write it in this way, as equal to nRT. So if suppose we multiply it by 3 over 2, and here multiplied by 3 over 2. So we remain with the NMU squared over 2 is equal to NR 3 over 2, 3 times NR 3 times nRT. Yeah, so we have it like that. Okay. Then there we might be interested with the suppose that we have 1 mole. Suppose we have 1 mole of gases. So here we will have the Avogadro number, that is equal to 3 RT over 2. Yeah. From there, if we divide it, and we divide by NA in both sides, so we have the resulting equation like that one. Yeah. M u squared over 2 is equal to 3 RT over 2N. Yeah. NA. Here this is kinetic energy. Knowing that here we have the division of this one by Avogadro number. So we will have the kinetic energy of 1 molecule. This is kinetic energy. This kinetic energy of 1 molecule. Kinetic energy of 1 molecule in a cube. So it will have such a. So if we want to find out the kinetic energy of one molecule in a cube, so we can use it. That formula. Then we have also it is from that relation on that relation that if we have mass times velocity squared, that is equal to 3RT over 2n. So if we divide both sides, by mass and then multiply by 2, so we have 3RT over 2NA times 2 over mass. So we will have this one is equal to 3t over n times. So we have NA. That is Avogadro. You know that usually mass is equal to number of moles. Number of moles times molar mass. So if we have molar mass. Now for this one, since it is an Avogadro number, we could say that this one is less likely. We have usually the formula that mass over molar mass. So if we substitute there, we will have 3RT over is just like molar mass. So if we find out the square root on both sides, we will have 3RT over. This is called relative mean square speed. Relative mean square speed of a molecule. So if you want to find out the relative mean square speed of a molecule relating to temperature and the molar mass, for a certain molecule, then we can use this one. For instance, we can find out the relative mean square speed of oxygen may be at 300 degrees. So if we want to find out the relative mean square speed of oxygen at 300 degrees centigrade, we know that the molar mass of oxygen is 32. So the temperature is 300. The ideal gas constant is known. Then you can just compute it easily. Now there, of course, suppose we have the relative mean square speed for a molecule 1 that it is equal to 3RT over molar mass. And we have another molecule too that it has this is maybe at the same temperature, that all of them are treated at the same temperature. They be within the same container, at the same temperature, within the same container. But you have two kinds of molecules, maybe of nitrogen and oxygen. Now we want to find, you have maybe the relative mean square speed of one of a molecule. We want to find out another one. Let us say maybe you have of oxygen. Here you have of oxygen. You want to find out of nitrogen. Okay. So it is only the matter of having a simple calculation. You take that one, divide by this one. So it's the same as having 3RT divided by 3RT. So this is for 1 and this is for 2. Now, this is the same as saying that you will have 3RT M1 times M2 divided by 3RT. So you will have the two having the relation of this kind, that you will have the square root of the molar mass of the second over molar mass of the first one. So they will rate with this. So suppose you have for oxygen, or you have for oxygen, you are looking for nitrogen. So you know the molar mass of oxygen, you know the molar mass of nitrogen, so it is only the matter of knowing, of making calculation in order to find out the one unknown value. Okay. So that is about kinetic field, where we will see that we have seen that it is trying to treat gases as particles, but you see that there are assumptions when it is in the container. There are assumptions there. That all of them are molecules, they are moving randomly, have elastic collisions, no energy which is lost, negligible volume, just like that. Then in trying to treat it mathematically, you see that we are trying to find out how the pressure, how those molecules will exert pressure relative to its motion when it is present in the cube, and also from there we have come out with the proof of Boyle's law. So mathematically, we see that it is related to PV times the number of molecules that are present, mass, the velocity. Then also we have the interest of also knowing what will be the energy of one molecule when it is in the cube. And lastly, the relative mean square speed. Now you will see that there is this the value of R. You have R, and all of them are constants. Avogadro number, I did guess on top, they give out a constant. That constant is known as the Boltzmann constant. Then after that we have we have been dealing with the ideal gases, those gases which show a behavior at high temperatures and low pressure. That ideal gases all will be ideal gases if they are under those conditions, high temperatures. But most of gases at a high temperature, at a low temperature and high pressure, we could say that they do not behave as ideal gases. We say that they are real gases. They are real gases, so they deviate from the ideal gas equation. There are some practical indicators. There are some practical indicators for real gases. One of the indicator is the relationship between pressure volume contact and the pressure and the pressure. Of course, in trying to have to plot a graph for pressure times volume against volume. What was expected is that if you have the measurements for pressure and you have the measurements for volume, then after that you multiply them. That you have pressure, you have volume, then after that you have PV, like that. So you have measurements for that. Then you try to plot that. What was expected was that plotting PV against P for ideal gas, for any gas which is ideal. There, of course, although the pressure increases, but that one remains constant. The product remains constant. So we will have a graph like that. A graph like that for ideal gas. Practically, it is proven that it is not like that. It's not like that. When you have maybe high pressure and have low temperature. For instance, for nitrogen, you see that at the first the pressure, as the pressure increases, the product increases, but it reaches a time when the pressure is very high, then the PV increases like that. So all of this you see that hydrogen makes a straight line. Oxygen also increases, but later on, as the pressure becomes very high, then it decreases. That is the deviation from one of practical indicator that shows that ideal gases deviate from reality. Another practical indicator, we have the relationship between compressibility factor against relationship between a compressibility factor against pressure for 1 mole of a gas. The compressibility factor is given as Z is equal to PV over RT. That is the compressibility factor. So it means, again, having the values of pressure, values of volume, and then having the data for this one. When trying to plot the graph, then we see that there was again variation. There was variation like that, variation like that. It was expected that for ideal gases, it would be a straight line. Would have been a straight line like that. That no variation as the pressure increases, and with that product there. That is, the pressure increases, here remains constant. So the pressure increase remains constant, so you have a graph like that. But it was not like that. That at a certain temperature, at 10 degrees centigrade, for a certain case, it was found that it behaves like that. Another temperature, at 20 degrees centigrade, it behaved like that. So to show that there is deviation of gases from ideal gas behavior. Another practical indicator is only condensation or liquefaction of gases. Usually we have gases being condensed and the gases being liquefied. If you can see from the graphs that when there is high temperature, here low temperature, then the temperature increases. We have the isothermal behavior of the system in relation with the variation of pressure and the volume, that it was expected to be like that. At that temperature, in all these graphs. But at high temperature, at a very high temperature, and of course that is where we said that most of the gases show ideal gas behavior at a very high temperature. So there is a good isothermal, a parabolic graph like that one. But as the temperature was decreasing, so that there was behavior. As the volume increases, it reaches a time there. Something they brought becomes very difficult. Then there you see that you increase the pressure, but the volume does not change. But yes, does not change. As the temperature becomes very low, like that. We have at a certain point again, the pressure increases, but the volume does not show changing. This area is the point of liquefaction for gases, that they are liquefied. Liquefied is the pressure becomes very high and the temperature becomes very low. So those three are among of practical indicators that show that gases do deviate from ideal gas behavior. But also there is another one that we say that when we have gases, we have gases which have two gases which have the same volume at a given pressure in the temperature, that all of them will have the same amount. But at STP, for 1 mole of gases, it was found that all of them will have for 1 mole be equal to 22.4 decimeter cubed. 22.4 decimeter cubed at STP. At STP. That most of them will have that. Practically it is being shown that you see that some of them will have 22.00, others might have 23.00. They do not have such amount. Just to show that there is practical indication that most of gases do deviate from that. Now, Van der Waals tried to derive equation that suits the real gases. Okay? He considered the actual volumes of gases. He considered the actual volumes of gases when are present in a cube or in a container. When they are present in a container, the actual volumes. If we consider the actual volumes occupied by molecules, which reduces the volume into which the molecules can freely move. Okay. That the molecules have a certain volume, and it is due to that volume that they tend not to freely move much. So it reduces the space to which the molecules could move. That volume which is reduced is NB, where B is the volume occupied by 1 mole of the gas. This is the volume of the container. The volume that is reduced due to the amount of gas is represented like that. Then he considered the intermolecular interactions between molecules that reduce pressure that is exerted on the walls of the container as a result of collision. It was found that pressure is proportional to collision frequency and the momentum of colliding particles, where all are squared proportional to gas density. Yeah. So we have the actual volume. There is actual volume of the gas, and there is actual pressure. Actual pressure is represented like that. B is a constant. Also, A is a constant. B is a constant, and A is a constant for a specific type of gas. Yeah. So treating it the same way as we treated the ideal gas equation, where we had the ideal gas equation having a pressure times volume, which is equal to the amount of the gas times the ideal gas constant times temperature. So even here we can multiply now the actual volume times the actual pressure, where we have it like that. All of them being equal to. So this is known as Van der Waals equation. As I have said, these are constants. These are constants. B and N are constants for a specific type of gas. Of course, we have temperature as the usual. Volume is the volume of the container as it is, and the pressure. That is the pressure that is measured, or that is found, and this is the pressure that is reduced due to the intermolecular actions. Yeah. Then, after having found about the real gases, then we can go to the last part about the properties of gas. Properties of gas mixtures. Suppose that we have several types of gases which are in a container. That we have a container maybe. We have a container. And in that container, maybe there is oxygen, there is nitrogen, and a certain inert gas like neon also is present. Even argon maybe that also is present. All of them are there. Now, according to Dalton's law of partial pressures, is that the total pressure of gases in the given volume of the container is the sum of the partial pressures of all the different gases in a mixture. And that is the law of partial pressures. It is represented by supposing that you have a gas A, you have a gas B, and you have a gas C. So the total pressures of all those gases make up the total pressure of the gases in the container. And the pressure of each gas, in that container is the partial pressure. So that is it, partial pressure. So we'll have the partial pressure A, partial pressure B, partial pressure C. So, of course, we have the pressure, which is the pressure, we have P is equal to PA, PB, PC, etc. So the pressure is represented as usual as the nRT over V. It's treated in the same way. And then we have also the partial pressure A is treated as a NA RT over V. Also PB will be treated as a NB plus NB RT over P. So suppose that we have these ones A and the B as what? As A and the B as the gases with the partial pressure A and the partial pressure B. So the total pressure for PA plus PB is equal to P. NA RT over V plus NB RT over V. T and V are treated the same because we as with the assumption that all of them are within the same container, so they have the same volume. Of course, these we treat them as ideal gases, so they have the same volume, and all of them are at the same temperature. So we have RT over V into Na plus NB. So we say that N RT over V is equal to PA plus P plus PB. Yeah. This is the total. This is the total pressure. This is the total pressure. And we have mole fraction. N is equal to Na plus Nb. So this is the total number of moles, the number of moles of each gas for A and then B. So we have something about mole fraction. Mole fraction. We could say that mole fraction, if we denote it as XA for a pressure A. Since we have its number of moles as Na. So the total number must be Na plus Nb. So it's the same as saying we have Na over N. That is the total number of what? Total number of moles in the container. So mole fraction, we present it like that. So if you have the mole fraction for gas A, and you have the total number of molecules that are present there, then you can find out the mole fraction. But we have that Na is equal to PA. V over RT. PV over RT. And we have N is equal to PV over RT. So we have the mole fraction XA being equal to Na over N. This is the same as saying that we have PAV over RT, divide it by PV over RT. Here we will have a PAV RT times RT over P. So mole fraction is equal to PA over P over P over P. So if we have partial pressure, and then we have total pressure, then we can find out the mole fraction for that one. And yet we can find out the partial pressure if we have the mole fraction and then we have the total pressure. Like that one. So that's how we can treat gases when they are mixed together. Yeah. So we have tried to go through the treatment of kinetic theory, where we have been treating gases as molecules, as particles in form of molecules, and we have come across the assumptions behind how the molecule, when it is in a cube, that as a molecule it will have a motion, will not have interaction, will have collisions which are elastic. Then we have tried to derive, to treat it mathematically in order to come out with how the molecules exert pressure in that cube. And it is the proof of Euler's law. Then after that, we have tried to find out the kinetic energy of a single molecule when it is in a cube, and the relative velocity, relative mean speed, velocity of a molecule that is in a container. Then we have also tried to see the real gases that when you have high pressures and you have low temperatures, most of gases will deviate from the ideal gas equation. So there was modification by Van der Waal, who came out with a new equation that considers the intermolecular attractions that reduces, that makes up a volume of the gases, and then also the pressure that is due to what? That is due to the interactions of the gases. Then lastly, about the properties of the gas mixtures, where we have the partial pressure law, that each gas, the total pressure within a container of all gases is the sum of the partial pressures of the gases within that container. So thank you. We shall meet in the next knowledge.